Right, done. Finally make a channel about what it takes to be an astrophysicist. But no. Let's propose slashing next year's astrophysics budget, and now Michael doesn't know if he can go to grad school. Oh, and let's take money away from NASA that we already gave to them, and then have to backpedal when we get pushback for it. You know you messed up when you got both sides of Congress to come together and pass a bill in less than a month. Well, what up, space nerds? I'm Michael. I'm a fellow space nerd at Arizona State University, where I study astronomical and planetary sciences and physics. Yeah. And because I'm a wannabe space dude, I watch a lot of videos. Probably too many videos. All right, we'll call it what it is. I watch an unhealthy amount of videos from people that know way more on the subject than I do. People like the OGs, Carl Sagan, Neil deGrasse Tyson alongside Lord Nice, Sir Stephen Hawking and Roger Penrose, Sabina Hassenfelder, and my personal favorites, Professor Brian Cox and Dr. Becky Smethurst. And I love when they put out those videos about what it takes to become an astrophysicist. How did they go from school through a career path to become a researcher? Because, like I said, they know way more on the subject than I do, so they only have one or two of those videos. Rightfully so, they focus more on current research or like that big picture idea. Well, that's where I come in. I'm here to answer the questions about how do I prepare to be an astrophysicist? How do you learn to do the research and use the instruments? Why am I listening to a 37-year-old improv comedian who still has a year left on his space math degree? I haven't told you any of that yet. So, since you're already in my brain, you might as well tell people I have a previous degree in psychology and significant back issues. I mean, look around. I am in the basements of YouTube. This is not a Hollywood production. My film quality is inconsistent at best. I haven't even checked my sound yet, and the lighting, oh my god, the lighting. I look like Casper's creepy uncle. But what you are going to get is someone who's actually going through the process of becoming an astrophysicist. Someone who knows what it mentally and physically takes. And you might be watching this and realize I love space and love learning about it. But I really don't want to go through all the math and physics involved because, spoiler alert, it's quite a bit. And that's completely fine. It is so much better to learn that now than spend tens of thousands of dollars and countless hours studying for something you realize isn't even your thing. That's completely fine. And in that case, hopefully I can get a laugh at you. Probably more so at me than with me, considering I just said get a laugh at you. But hey, as long as you're entertained.
Are you not entertained? Are you not entertained? Is this not why you are here?
I'm assuming you like to be entertained, probably laughing. And if you're anywhere near Raleigh, North Carolina, you can do both at ComedyWorks. And to find out more information and purchase your tickets online, you can go to comedyworks.com. That's ComedyWorks with an X.com. I've had to say that a lot. Anyway, I think the best way to premiere this channel is by taking you along with me on our first observing run to Kitt Peak National Observatory for my class Research Methods in Observational Astronomy. All right, this is a 3-week class in which we visited the largest meteorite lab outside of NASA, Meteor Crater, which is the most well-preserved crater on Earth, Sunset Crater, which is a different type of crater, the Grand Canyon, which is like a bunch of craters next to each other, the Lowell Observatory, where Pluto was discovered, and of course that observing run at Kitt Peak National Observatory, where we're going to study star-forming regions in colliding galaxies and exoplanet transits using the Bach 2.3 meter telescope. That's 90 inches in American. See, you've met my editor. Say hi to other Michael. Oh, what up? Since he's so rudely interrupted, might as well take care of other business because this video is
presented by no one.
Oh, come on, Ernie.
Unsullied by sponsorship since
1989. Oh,
I was born in 88. Dude, are we sponsored for the first 6 months of our lives? Mom! Mom!
What?
Was I sponsored for the first 6 months of my life?
You're an idiot.
He's absolutely right.
Sorry. Funny thing is, I had to convince her to say that. And even after she did, she was like, I didn't like saying that. I thought it was funny. It was pretty funny. Thanks, dude.
Michael,
So,
focus.
oh, right, observing run. So I'm going to get into way more detail about this later, but we observe those star-forming regions in colliding galaxies using emission spectra, and we observe the exoplanet transits using the transit method. Yeah. Anyway, I'm all packed. Bags are in the car. You know what that means.
Leaving on a jet plane. I don't know when I'll be back again.
Oh, and for all those people who are like, oh, most Americans don't have passports. They must not like visiting other countries or seeing other cultures. Really don't think that's true because I just made all that up. Well, now that I said it, it actually sounds really true. But it's important to remember we have a very large country with many climates and many cultures. And this is about a 5-ish hour flight, 2,000 something miles slash kilometers. Help me out of the Michael. This is a small portion of the country. It's just the bottom part. We're going from the southeast, basically through the desert to Arizona.
Man, you said that this trip already happened. This is obviously fake. Man.
Pretend. You should know from TV by now that this is all fake. It's called editing. Speaking of editing, are you ready for a poorly put together montage that probably goes on for way too long? Dude, I mean, true, but damn. Fine, this is now your outro. Fair enough. What, I need to carry you? Lazy. All right, now that we landed in Arizona and I've created an identical filming space, let's get down to the schedule. So the trip is broken up into 3 parts. The first 4 days are spent on ASU's campus. We have our meet and greet with the crew. We take a tour of the campus. That's right, I said a tour of the campus because every one of us but one are online students. So for all those people who are like, oh, what are you going to do online? How's your observing run going, huh? Glasses didn't go on right. The second day, we hit up the Meteorite Lab to get ready for our visit to Meteor Crater, and then we meet up with the professors of CC, which is the School of Earth and Space Exploration. I guess they thought say sounded too much like Foghorn Leghorn. The third day, we choose our viewing targets and learn how to plot their coordinates. Fourth day, we're going to learn about the instruments we will use and the software to bring our data to life. And then after that, we have what I like to call our amateur astronomy night, where we map the night sky so we can compare the sky in Tempe to Kitt Peak to Flagstaff. Again, this helped with our schedule. And the reason I'm saying the schedule, because I know there's going to be a lot of people that are like, oh, I work a midnight shift, you're just being a baby. Probably, I'm not going to lie. But when you're not used to it, and then you have to wake up at 2 p.m. and end your workday at 6 a.m. for 4 days straight, it gets to you a little bit mentally, especially when you're doing calculus and astrophysics. The second part of the trip is the next 4 days at Kitt Peak. So we arrive at Kitt Peak and we tour the observatory. We see all of the telescopes. We look at the one that we're going to use. And if you're familiar with DESI, the Dark Energy Spectroscopic Instrument, that's up there as well. It's on their 4-meter telescope. We have our second amateur astronomy night, where I can tell you one thing, the sky is very different at Kitt Peak than it is to Tempe. Here we actually had a few students that brought their own telescopes, and these are serious ones. They're EV telescopes, along with another one from the school. And these were some of the images that we got that night. The next day we learned how to use the telescope by viewing our targets that we selected back in Tempe. The third day we spent doing our exoplanet research, and the fourth day we spent with galaxies. Alright, day 9. Now we leave Kitt Peak and head to Flagstaff. On the way there, we stop at the University of Arizona and look at the Mirror Lab, which is where they make the mirrors for all of the big telescopes. Then the next 2 days, we spent just straight sciencing and mathing, learning how to analyze all the data that we just received. Day 13 is all about craters. We head to Meteor Crater, which is an impact crater. We go to Sunset Crater, which is a volcanic crater. And then we go to Reupload National Monument. Our 5th day in Flagstaff was spent sciencing and mathing again. The 6th day is our Lowell Observatory day. So we have our Lowell Science Tea, where we talk to all the researchers and professors that are there. We take a tour of the observatory. And then we go to what I like to call the Space Nerd Play Space, which is my words, not theirs. And then we have our final amateur astronomy night. Day 16, we work on the rough draft of our papers and begin preparing our presentations. Day 17 is the grandest of canyons, no explanation needed. Day 18, that is our last full day, and that is when we give our presentations. Alright, administrative stuff done. Time to get to the good stuff. Oh, what the hell are you doing here? No, I don't want to hear any of that.
Why?
No. Because my people are smart people. They're watching videos on how to be an astrophysicist. 99.5% of videos have told people to do that. I think they know. Comedians are even naming it their special.
I get at the store, but I have to let them know to like it.
One more word. One.
Well,
Don't- Ridiculous. So I thought I was going to be the oldest one on this trip. I was 36 at the time. I thought I'd be the only one with imposter syndrome, and I thought I would be the dumbest smart person there. And after the whole trip, the only thing I'm sure about is I'm definitely the dumbest smart person. So now I think it's time to introduce you to the crew. And I know you hear that epic music building in the background. It may or may not be because I want my friends and I to have an epic introduction into something, and I don't know if it'll ever happen again, so why don't you ease up and get off my back, alright? God! Jeez, 3rd degree. Just trying to show you a picture. And boom! Oh, come on, dude. That's the picture we're using. Really? Come on, we gotta do something. Yeah, I'm on it. That was awesome, dude. All right, second day. Time for the meteorite lab. Every single rock in this room came from space. The majority of them obviously from the asteroid belt, but some from the moon and Mars. And I know a lot of you have heard this. If you were in the asteroid belt, you probably wouldn't have even known it. It's not as dense as people think. Pretty sure he said that if you collected all of the asteroids in the asteroid belt, it'd be about the fifth of the mass of the moon. Of course, Michael remembered wrong. It's 5% the mass of the moon, not 1/5 the mass of the moon. Get it together! ASU's meteorite expert is this dude, Dr. Lawrence Garvey. And there isn't a single question about meteorites that this dude doesn't know the answer. We challenged him. He won.
Man, you said this was the largest meteorite site outside of NASA. You're such a wannabe space dude. There's only like 30 rocks there. Man.
Oh, I'm sorry. That's just what's visible. Besides the stuff that's currently being researched on that's not even in that room, why don't we look at this? How about this entire wall? Or maybe the lockers to my right. Or how about this entire wall? Still not enough? How about under every single one of these tables? And before anybody says, oh, those must be tiny to fit in there, that doesn't count. Do you remember the big-ass crater that we're going to see that's almost a mile wide? That's the largest piece that was discovered. And for reference, that's Cody. That's because 99% of the meteorite turns into this. These contents are out of this world. Jar not included. See meteorite site for details. The reason we're looking at all of these, other than them just being awesome, as you can see from our faces, is to study also what it takes to make a crater. The size of the crater can depend on either the mass of the meteor or the velocity at which it's going, or both, obviously. And this is the selfie meteorite. Unfortunately, it is not gold. It is a stony iron meteorite, exposed to sunlight, oxygen, a whole bunch of stuff to make it look like this, and then shined up nicely. Still, awesome. Another thing is that all of these meteorites started at the same time the planets and the sun did. We all started from the end of another star's life. So now we can know what materials came out of that previous star. Once we reluctantly had to leave the meteorite lab, it was time to meet with the professors of CC. So we talked to them about their research, current classes we're in, grad school aspirations with the budget. Yeah. And then that was it. It was an easy day. And I want to make sure you realize this. We're normal people too.
Come here, Mr. Coyote. Yeah, we're those stupid people trying to tell you, hey, come here, Coyote.
We like to go out and have fun. So that's what we did that night. We don't just sit around talking about space and doing calculus all day. We do like to go out and talk about space. That usually doesn't change.
It's yelling at me. No, it's not. Yes, it is.
All right, day 3. Now it's time to get into the good stuff. Probably the toughest one of the first 4. Hold up, Michael. I'll say something. You're probably going to be intimidated by what you see when you go in. Every single one of us, without a doctor in front of their name, was intimidated at least 50% of the time. This is one thing that the more you do, the more comfortable you get, and the more comfortable you get, the more confident you get. And then you just start doing it without thinking. We choose our targets that we're going to view, some of the galaxies, exoplanets. We also learn how to plot their coordinates. We're going to start with a simpler type of coordinate system. This is called the horizon coordinate system. So you'll see directly above us is the zenith, and directly below is the nadir. Connecting the north and the south above us is the meridian. If we're looking at a star like this one, we can just look up and call that the altitude. Simple enough. Directly above us at the zenith is 90 degrees, and directly below us through the ground is the nadir at negative 90 degrees. Now if we want to see where in the sky it is, we start at the north and go clockwise around to where we have the altitude set up, and that is called the azimuth. We then put degrees like we would in the circle. We start at north, 0 degrees, 90, 180, 270. And that's the horizon coordinate system. It's also known as the altitude azimuth system, or the alt-az. Now this is the part that usually gets people. I know for sure it got me, and it got a bunch of other people. It is declination and right ascension. Declination is much easier, that's okay, but right ascension... Right ascension and declination are basically the latitude and longitude of the sky. We'll start here with the coordinate system that we all know, where we have the parallels of latitude and longitude. The equator is at 0 degrees latitude, and the prime meridian is at 0 degrees longitude. Now what we're going to do is extend that out into space. So above us, we have the north celestial pole, and below us, the south celestial pole. And the equator, we're just going to keep it where it is, but expand it out, and that becomes the celestial equator. We are tilted on our axis. This is a comparison to how it is in space to what we see on the ground. As you can see, that celestial equator is actually above us a little bit. Now we're going to add the parallels of declination. These are very similar to latitude. As you can see, this is why I was saying declination isn't as bad. The celestial equator is 0 degrees. Going north would be positive degrees, and going south would be negative degrees. But now we're going to add the ecliptic. And the ecliptic is the path the sun travels through the day. But we have to pick a specific day, so we pick the vernal equinox, which is the first day of spring in the northern hemisphere. You can see where the ecliptic and the celestial equator meet at the vernal equinox. That is going to be basically our prime meridian, our 0 of right ascension. Speaking of right ascension, we now break the sphere up into longitudes, where we start right at that point, the vernal equinox. That is our prime meridian. And we count counterclockwise all the way around to make a 24-hour system. So instead of doing 360 degrees, we do 24 hours. Rigel has a right ascension of 5 hours 15 minutes and a declination of 8 degrees 12 minutes. Just like in regular time, hours can be broken up into minutes, that is sort of their decimal point, and degrees can be broken up into minutes. One thing I get tripped up about is the LST, which is the local sidereal time. Sidereal day is a full day in relation to the stars instead of the sun. So as you can see here, it takes 23 hours, 56 minutes, and 4 seconds to do a complete revolution. But since we are orbiting the Earth, we have to compensate for that difference, and that adds that extra 3 minutes and 56 seconds. So in order for us to get the actual proper coordinates, we must incorporate it into sidereal time. So we have to know what our LST is to get the correct right ascension. Here we're beginning to choose our targets. These are our galaxies. The website we're using is airmass.org. You'll see Object, M45, stuff like that. Those are the names of the galaxies. And we just learned about the RA and the declination. We then can click on Simbad, which will take us to another system that will show us the coordinates and give us a picture in a star map. Now we choose our exoplanets. This is from swarthmore.edu at Swarthmore College. It shows us the name, obviously, of the exoplanet. It will give us the right ascension and declination. It'll also give us the duration of the transit, so how long it will spend in front of its star, as well as the period, which is its year, how long it takes for it to go around its star. But the most important thing here is the exoplanet watch rank, which we are trying to choose ones higher up so that we can fill in more data about the unknown transits. Now we move on to the software we use to bring that data to life. This is called DS9. We load our data in here and it creates our images. As you can see from the beginning image, it's not exactly clear, so we're able to change the contrast, change the different type of filters that we use to make it a little bit easier to view. But because the human eye and brain work best with differences, distinct differences rather than black to gray to white, we can also put it to color, like Predator. So this now will show us differences in gases or different types of light, whatever it is we're looking at that point.
Michael,
Yes, sir.
all of the sitting is not good for your back. You knew that.
Yeah, I know it. I'm in pain, dude. I'm always in pain. Alright, fourth day. Time to learn about the instruments we're going to use. So we're going to use the 90 prime instrument and the B and C spectrograph. So the 90 prime instrument is a CCD, which stands for a charged coupled device. Now, a charged coupled device is actually how your cell phone camera works. The way it is it is broken up into pixels, just like your phone has megapixels, which is 1,000,000 pixels. That's what these are. A photon will come in and excite an electron. We're able to then collect all those electrons like you would on an extended exposure on your phone where you can take a picture for 10 seconds. We can do this for a very long time. So that is how we see the light that we can't see with our eyes. We just collect it all together. Here is the 90 prime CCD. Putting the star in the middle where our focus is not going to work because it is broken up into 4 parts. So what we have to do is move our star into one of the panels. If you look at the CCD1 in the top left corner, you'll see that bright star. You'll also see that each one is broken up into 4 panels. So ours is in the bottom right corner of CCD1. Okay, now over to the B and C spectrograph. So the way a spectrograph works is it breaks light up into its component wavelengths, just like you see here, and then we can take data from it. I've always wondered how this actually works in a telescope. So, here's an animation of the spectrograph that's on the James Webb Space Telescope. Light will come in usually through 1 or 2 slits. It will then bounce off a few mirrors and go through a filter of whatever you choose based on what you're looking for. Bounce around a few more mirrors and then finally hit the grating that splits it up into its wavelengths, and then we study that. And this is the type of information we get from that spectrograph. On the left you'll see a continuous spectrum. This is just straight light that has nothing interfering with it at all. The emission spectrum, which is what we will be working with, is in the middle, and that shows just what light is being emitted out. And then the absorption spectra on the right is showing what light is missing that is passing through. So the one on the right, the absorption spectra, is basically how we find exoplanet atmospheres. We see light traveling through the atmosphere, and then we can tell what the atmosphere is taking from it. We are studying hot gas, which emits its own light, hence emission spectrum. By the way, if you want to know what space nerds are mentally going through after 2 consecutive 8-hour days learning about astrophysics, it's this. Only thing left to do was the amateur astronomy night. Now we went to a mountain which is next to Arizona State's campus, and I put mountain in quotes. Now sorry, don't mean to, rip on a mountain, but it's more of a very large hill. It still did the trick. We had a great view over the whole Phoenix metropolitan area. The sky in Tempe is not exactly the best for stargazing. The light pollution is very bad. But I think this is funny. We had probably the most gangster looking picture here with Kiana. I love this picture. And the picture that probably makes us look like the nerdiest people on the face of the earth, with all of us with just red headlamps. And that's it. After that, we went to bed as late as we could because we knew we'd be waking up early to go to Kitt Peak, trying to get used to that schedule. That kind of backfired when we almost all fell asleep on the bus. Yeah. So that's it for part 1. Thank you so much for coming along with me. I'm hoping to get the next video out, like right after this one. Future other Michael. What? Do you think you can get the next video out, like right after this one? Yeah, sure. Who needs sleep? I don't need sleep. I haven't slept in 26 hours. I'm waiting on the footage to be clear, dude. You'll figure it out. That's my boy. I tip both caps to you, sir. All right. Can't wait to see you guys again. Like I said, the next video is going to be coming out very shortly after this one, hopefully in the next hour or so. It might take a little bit. It'll come when it comes. That's about all I got for you. Goodbye. You know, Brian Cox might be the only person that when he speaks, he could have my absolute full and complete attention, or he could put me to sleep in less than a second. I don't know anybody else like that. Maybe Morgan Freeman. I'm gonna have some weird dreams tonight.